Wrinkles in Time. Witness to the Birth of the Universe by George Smoot and Keay Davidson.
Oh, man.
Yeah, that is our starting point today. So the purpose of this deep dive is to explore this book and introduce this exact central question. How did almost imperceptible variations in the early universe become the cosmic seeds from which galaxies, stars, planets, and the observable structure of the universe eventually emerged?
Right, because, I mean, if you think about it, imagine you're holding just a perfectly smooth, polished bowling ball,
Okay.
and you find this microscopic scratch on its surface. And then you realize that if that tiny, tiny scratch didn't exist, well, neither would you, or the Earth, or, the entire Milky Way galaxy. That is the sheer scale of the cosmic mystery we're digging into today.
Which is why I think this discussion is going to be so much fun.
Oh, absolutely.
So just to give everyone a quick roadmap for the next bit of time, we are going to trace how cosmology made this massive leap from purely philosophical debates about our origins into a rigorous, testable science. We'll explore the historical hunt for the cosmic microwave background. We'll dive into the staggering team effort behind NASA's COBE satellite to actually map it.
Yeah.
And figure out how gravity drove the growth of the cosmic web from there.
And then, we'll look at how the high-resolution follow-up missions, WMAP and Planck, really brought everything into super sharp focus later on.
Exactly. And the book itself, Wrinkles in Time, it's an incredible source for all this.
It really is. Because it doesn't just deliver the dry cosmology, right? It acts as this the scientific history and a really personal first-person lens into the grueling, day-to-day reality of astronomical discovery.
Yeah, and we should definitely establish our guides for this material right up front. So George Smoot is the principal scientific participant who really drives the narrative here.
Right.
And Keay Davidson is the canonical co-writer who, helps structure this immense endeavor into something we can all actually grasp. But I want to throw a massive caveat in here right at the start.
Okay, what is it?
Reading this, we really, really need to reject that lone genius trope that the media always loves to cling to.
Oh, right. Yeah, totally.
Like, monumental science doesn't happen with just one guy looking through a telescope in the dark. It requires a massive coordinated system of rigorous skepticism, engineering, technical redundancy. This was a collaborative scientific triumph, not some solo mission.
Yeah, that context is so vital. You cannot have one without the thousands of others. And to appreciate why this collaborative triumph shifted our entire understanding of reality, I think we first have to look back at the state of cosmology before these measurements were even, possible.
Right, because for centuries, questions about the origin of the universe were basically trapped in the realm of philosophy.
Exactly. You couldn't test the universe's beginning. I mean, how could you?
Right, you can't exactly put the entire cosmos into a laboratory beaker to see what happens when you heat it up.
No, you definitely cannot. But in the 20th century, two major conceptual breakthroughs finally made cosmology a testable science. First, observations proved that the universe is actively expanding.
Right. Hubble and all that.
Yes. And second, theorists developed the hot Big Bang model.
Yeah.
And the logic there connects so beautifully, because if the universe is expanding today, well, running the clock backward means it must have been smaller, denser, and just unimaginably hot in the distant past.
It makes perfect sense when you put it like that.
Oh, right. And if it was essentially this cosmic furnace back then, it had to leave behind some measurable relic radiation.
Which perfectly sets up the central intellectual tension of our deep dive today.
Yeah.
Because when scientists eventually did find that relic radiation, it painted a picture of an early universe that was extremely smooth.
Yes. Very, very uniform.
Uniform and homogeneous. Like, everywhere they looked, the temperature was virtually identical.
Down to a fraction of a degree.
But, just look out a window today. The modern universe is incredibly lumpy.
It's extremely lumpy.
We are surrounded by highly structured clumps of matter. We've got galaxies, massive galaxy clusters, these vast structural filaments connecting them. And then, on the flip side, enormous, terrifyingly empty voids.
Right.
So the big question is, how do you start with perfectly smooth soup and end up with a highly structured cosmic web?
And the answer to that is entirely hidden inside that relic radiation we mentioned, what we call the cosmic microwave background, or the CMB for short.
Let's define what that actually is for a second.
Sure. So the CMB is the afterglow of the Big Bang. It is the radiation that was released when the universe finally cooled just enough to become transparent, which happened roughly 380,000 years after the Big Bang.
Okay.
Cosmologists call this specific era recombination.
Okay, let's unpack this, because recombination sounds like a I don't know, a biological term or something. What is physically happening to the atoms in the universe at that exact 380,000 year mark?
So before that specific mark, the universe was so insanely hot that atoms couldn't even hold themselves together.
It was just too energetic.
Way too energetic. It was a dense plasma. So you had electrons and protons just flying around independently. And because free electrons are really, really good at scattering light, photons, which are the basic particles of light, they were completely trapped.
Oh, I see.
Yeah, they would move a fraction of a millimeter and just crash into an electron, bouncing around like pinballs in a machine.
So the light couldn't go anywhere.
Exactly. The entire universe was this opaque, glowing, ultra-dense fog. But at roughly 380,000 years, the continuous expansion of the universe caused it to finally cool down to about 3,000 degrees Kelvin.
Which I'm guessing is finally cold enough for those free protons and electrons to slow down, grab onto each other, and form stable, neutral hydrogen atoms.
Yes, that is exactly it. The pinball bumpers just disappeared.
Wow.
We call this the moment of last scattering, because those trapped photons were finally free to just travel in straight lines through space, and honestly, they've been traveling ever since.
That's incredible. Just flying through space for billions of years.
Right. Now, because the universe has continued to expand for all those billions of years since, the very fabric of space has stretched those ancient photons out. So their wavelengths elongated, shifting them all the way down into the microwave part of the electromagnetic spectrum.
Got it. So they started as, what, visible light or something hotter?
Much hotter. But by the time they hit our detectors today, that once blistering radiation has cooled to roughly 2.7 Kelvin, which is just a whisper above absolute zero.
You know, it's really common for articles and stuff to call the CMB a baby picture of the universe.
Yeah, you hear that all the time.
But I feel like that phrasing causes a lot of confusion. Because when you hear baby picture, you naturally imagine, snapping a conventional optical photograph of physical objects.
Yeah.
Like you're looking at tiny glowing baby galaxies or something.
Which is definitely not what it is.
Right. Looking at the CMB is really more like looking at the glowing fog of the early universe finally lifting. You aren't seeing formed objects yet. You are seeing the boundary line where the fog cleared and the light first escaped.
That is a brilliant way to frame it, actually. You are viewing a surface of last scattering through microwave radiation. You are not looking at a physical surface of solid matter.
So, if the hot Big Bang theory was right, this relic radiation absolutely had to exist. But more than that, it had to match a very specific mathematical shape, right?
Exactly. It couldn't just be any radiation.
And the problem was, we couldn't measure it accurately from down here on Earth.
No, we couldn't. The Earth's atmosphere is an absolute nightmare for microwave astronomy.
Because of the weather?
Because of water vapor, mostly. Water vapor absorbs microwaves. And also, just the planet itself emits a ton of thermal noise. So to prove that this radiation matched the Big Bang's exact predictions, we had to get above all that. We had to go to the pristine vacuum of space.
And that necessitated NASA's Cosmic Background Explorer, COBE-B, which launched in 1989.
Yes, COBE-E.
And I really want to emphasize the sheer scale of the NASA Goddard team behind COBE here. This required an army of engineers, data analysts, instrument specialists, and the wider COBE collaboration. Like the rigor required to build a satellite that functions flawlessly in the freezing void of space with thousands of people cross-checking each other. It's just staggering.
Oh, the engineering was a marvel. Just a total marvel. And the satellite itself, it carried 3 distinct instruments, each with its own massive, dedicated team.
Let's walk through those.
Well, the first one we should discuss is FIRIS. That stands for the Far Infrared Absolute Spectrophotometer.
FIRIS, okay.
Its primary mission was to measure the overall spectrum of this relic radiation. So it operated by scanning the sky and then constantly comparing the incoming microwave spectrum against an internal, perfectly calibrated reference source on the satellite itself.
Which resulted in finding a near-perfect black-body spectrum.
Yes.
But for anyone listening who isn't a physicist, what does a black-body spectrum actually prove? Like, why is that such a big deal?
What's fascinating here is why this specific thermal history is the ultimate smoking gun for the Big Bang. A blackbody spectrum is this very precise mathematical curve. It represents an object that is in perfect thermal equilibrium.
Okay.
Its shape depends entirely, and I mean only on its temperature, nothing else. So FIRIS plotted the incoming CMB data, and it matched this theoretical Big Bang curve so flawlessly that the error bars on the graph literally disappeared into the thickness of the printed line.
Wait, really? The error bars were smaller than the ink on the page?
Literally smaller than the ink. It was that perfect.
Meaning the universe wasn't just, kind of hot in the past. It followed the exact thermodynamic rules of a dense, expanding plasma.
Precisely. And this specific work, which was heavily championed by John C. Mather, who, by the way, would later share the Nobel Prize with George Smoot for this moved the Big Bang from a very strong theoretical model to an observable physical reality.
That is huge. But, ironically, a perfect black-body spectrum actually deepens our cosmic puzzle.
Oh, it really does.
Because if the temperature of the early universe is perfectly uniform everywhere, then the matter in that universe must have been perfectly evenly distributed too.
Right.
But if matter is perfectly even, gravity pulls on every particle equally in every direction. It's just a cosmic stalemate.
Nothing moves.
Right, nothing would ever collapse to form a star, let alone a whole galaxy. Kobe had to find imperfections in that smoothness, or else our very existence makes absolutely no sense.
Which brings in the second instrument on Kobe, the differential microwave radiometer, or DMR.
Okay, so FIRES did the overall spectrum and DMR did what?
FIRES looked at the overall spectrum, yeah, but the DMR was designed specifically to search for large-scale temperature anisotropies.
Anisotropy.
Yeah, anisotropy simply means a variation depending on the direction you look. So the DMR had these microwave horns pointing in different directions, and it was constantly comparing the temperature of one patch of sky against another patch of sky, just hunting for microscopic differences.
And it took them years of scanning, right? But they eventually found them.
They did.
Though calling them differences almost overstates it, I feel like. We're talking about temperature variations of roughly 1 part in 100,000, right?
It is an unbelievably faint signal. We are talking about a tiny, tiny fraction of a degree. These are what cosmologists call primordial perturbations.
And these perturbations are the quote-unquote wrinkles referenced in the title of the book.
Yes. But the book uses wrinkles as a metaphor for the general public, and we need to be very, very careful to define that here.
Yeah, let's clarify that.
When they talk about cosmic wrinkles, they are solely referring to these tiny temperature and density differences in the primordial plasma. They are absolutely not talking about literal folds or creases or physical cracks in the fabric of space-time itself.
Okay, I have to stop and ask how they even knew they were looking at a real signal. Because the temperature difference of 1 part in 100,000 seems like it would just get completely drowned out by literally everything else in the universe.
Oh, it was!
Right, like how do you measure a microscopic variation in a signal that is already just a faint microwave whisper to begin with?
It was an agonizing, years-long mathematical extraction process. The actual cosmic signal was buried under just towering layers of noise.
Where was the noise coming from?
Everywhere. The team first had to model and mathematically subtract the DMR instrument's own internal thermal noise.
Okay, that makes sense.
Then they had to adjust for calibration drifts over time, because the instrument changes slightly as it ages in space. Then they had to subtract local contamination from our own solar system.
Wow.
And the most daunting hurdle of all was our own Milky Way galaxy.
It's just getting in the way.
Basically, yeah. The dust and the electrons in our galaxy emit their own radiation, which creates this massive blinding glare right in the middle of the sky.
This is where the third instrument comes in, right? DIRBE.
Yes, the Diffuse Infrared Background Experiment, or DRRB. This instrument studied diffuse infrared radiation. Its data was incredibly valuable for mapping out all that interstellar dust in the Milky Way.
So they use that to basically create a map of the glare.
Exactly. It allowed the analysts to create a template of our galaxy's foreground emission. And then they mathematically subtracted that galactic glare from the microwave maps to reveal the true cosmological background hiding behind it.
That is wild to me. It's like trying to record the sound of a pin dropping in the middle of a hurricane while someone is playing a trumpet directly into your microphone.
That's a pretty good way to put it.
You have to meticulously record the hurricane and the trumpet and then run some insane audio algorithm to delete them perfectly just to hear the pin.
Yeah, that's exactly what they did, but with light.
It really highlights that those familiar, colorful oval maps of the CMB we always see in articles, those aren't raw optical photographs snapped by a space camera.
Not at all.
They are highly processed scientific visualizations. They are the output of a massive computational pipeline.
That distinction is so crucial. Once they peeled away the hurricane and the trumpet, they finally had their isolated pin drop, the wrinkles. But finding them only answers the first half of the mystery.
Right, because we still have to get to the galaxies.
Exactly. The next monumental question is, how did a density difference of 1 part in 100,000 physically grow into the colossal, highly structured cosmic web we live in today?
And here's where it gets really interesting. Because you can't just take a slightly warmer patch of plasma, wait a few billion years, and expect a galaxy to pop out.
No, the physics just doesn't work that way.
Right. Because ordinary matter, what cosmologists call baryonic matter, the protons and neutrons making up our bodies, the planets and the stars, that stuff couldn't clump together in the early universe. It was locked in that hot plasma, constantly being blasted apart by the intense radiation pressure of all those trapped photons.
Which means we are missing a massive ingredient here, non-baryonic dark matter.
Ah.
This played the ultimate critical role. Dark matter, by definition, does not couple with light the way ordinary matter does.
Meaning light just passes right through it.
Pretty much. It ignores photons entirely. So because it ignores them, it was completely immune to that intense radiation pressure bouncing around in the early universe.
So while all the normal matter was getting pushed around and prevented from clumping, the dark matter was just free to start collapsing under its own gravity.
Exactly. Dark matter could begin to clump together gravitationally hundreds of thousands of years before ordinary matter could even start. It acted as an invisible gravitational scaffolding.
I love that image. Scaffolding.
Yeah. So those tiny temperature perturbations measured by Kobe's DMR, they actually correspond to areas where there was slightly more or slightly less dark matter.
So what does this all mean? Let me see if I can synthesize this gravitational chain reaction based on that.
Go for it.
Okay, so in the very early universe, you have these slightly overdense regions, which are essentially invisible dark matter gravity wells.
Right.
Because they have just a tiny bit more mass, their local gravity fights against the expansion of the universe, pulling in even more dark matter. Then we hit that 380,000-year mark. Recombination happens.
Yeah, the fog clears.
The universe cools, the photons escape, and suddenly that intense radiation pressure just drops to zero. Now, ordinary hydrogen gas is finally free to move, and it immediately gets sucked down into those pre-existing dark matter gravity wells.
Spot on.
And as it falls in, the gas compresses, it heats up, and it ignites to form the very first stars.
You've nailed the sequence perfectly. Those first stars group into galaxies inside those deep dark matter wells, and then the galaxies group into massive clusters, and they trace out vast filaments, constantly pulling matter away from the underdense regions.
Which leaves behind the voids.
Yes, leaving behind enormous, empty cosmic voids.
But I imagine it's really easy to look at a map of the CMB and misunderstand what it's actually showing. Like a red hot spot on that map isn't literally a baby picture of the Milky Way, right?
No, we must make that explicit distinction. A single hotspot on the CMB map is not simply one future galaxy waiting to bloom. The map is not a one-to-one blueprint for individual stars or individual galaxies.
What is it then?
It is a vast statistical map of early density. So a broad, overdense region on that map might eventually act as the seed for an entire supercluster containing thousands of galaxies, while a slightly underdense blue spot will slowly evacuate its matter over billions of years to become a deep cosmic void.
Okay, that makes a lot of sense.
Yeah.
So we've traced the structure of the universe back to the primordial wrinkles, and we know how dark matter and gravity amplified them over time.
Right.
But that forces an even deeper question, which I know cosmologists immediately started arguing about the second Kobe's data came out.
Oh, the theoretical debates were intense.
What caused the wrinkles in the first place? Like, how did the universe get slightly perturbed before it even became a plasma?
This raises an important question, and it brings us to inflationary theory, which is the leading theoretical framework for explaining the origin of those initial seeds. Inflation proposes that in the absolute merest fraction of a second after the Big Bang, the universe underwent a brief, incredibly violent period of accelerated exponential expansion.
Like faster than light expansion.
Yes. And during this hyperexpansion, microscopic quantum fluctuations, which are the tiny random jitters of energy that just constantly exist at the subatomic scale, they were instantly stretched to macroscopic cosmic scales.
Wait, are you saying the largest physical structures in the universe today, like the superclusters that contain trillions of stars, are literally just magnified quantum static from the beginning of time?
That is the staggering premise of inflation. It's wild, but that's what the math suggests. And what Kobe found supported this framework. The large-scale uniformity of the universe, combined with the specific statistical pattern of the anisotropies that the DMR measured, it perfectly matched the broad expectations set by inflationary theory.
But we should be clear about what Kobe didn't do, because the media got pretty wild with the headlines back in 1992.
Oh, they certainly did. We have to state the scientific limitations clearly here. Kobe supported the general concept of inflation by showing a near-flat geometry and scale invariant fluctuations, but it did not prove every theoretical model of inflation.
Because there are a bunch of different models, right?
There are many variations of the theory, nor did Kobe directly, quote-unquote, photograph quantum fluctuations themselves. It simply provided a statistical pattern of temperature variations that aligns beautifully with inflationary predictions.
Right, it's model-dependent inference, not a direct picture of a quantum jitter.
Exactly.
But science never stops with just one satellite, though. Once Kobe proved these wrinkles existed, the community didn't just pack up and go home.
Definitely not.
How did we get from Kobe's initial, famously blurry map to the incredibly high-definition pictures of the CMB we have today?
Well, the scientific community knew they needed much sharper vision to extract more data. Kobe proved the signal was there. The next step was precision. This led to NASA's WMAP satellite, which launched in 2001, and the European Space Agency's Planck mission, launched in 2009. These satellites were designed to map the exact same primordial structure, but with vastly greater angular resolution and instrument sensitivity.
So where Kobe's map looked kind of highly pixelated, WMAP and Planck brought the early universe into incredibly sharp focus.
Yes.
And it wasn't just about taking prettier pictures, right? Getting that high-definition data allowed cosmologists to measure things Kobe couldn't even see.
If we connect this to the bigger picture, these later missions entirely revolutionized cosmology by analyzing what we call acoustic peaks.
Acoustic peaks. Like sound.
Exactly like sound. In the early plasma, the pull of gravity and the outward push of radiation pressure created actual sound waves. Massive density oscillations just ringing through the universe.
Like a giant cosmic bell.
Exactly. And just as the harmonic frequencies of a bell can tell you the exact mixture of metals it's made of, the specific frequencies, the acoustic peaks of these primordial sound waves, tell us the exact composition of the universe.
Oh, wow.
Yeah. Studying these peaks at high resolution allowed cosmologists to refine the lambda cold dark matter model. They could mathematically pin down the exact percentages of ordinary matter, and dark energy.
That's incredible. So we should make it clear that WMAP and Planck didn't make Kobe irrelevant in any way.
Not at all.
They strengthened modern precision cosmology, building directly on Kobe's foundation. They refined its historic role by proving that the initial detection was real and that those vital wrinkles were exactly where they needed to be.
They were the logical, necessary successors to a paradigm-shifting discovery.
You know, reflecting on everything we've pulled from the sources today, it strikes me just how much the popular retelling of this story gets distorted over time.
Constant.
We've touched on several of these already, but I think we need to explicitly correct a few major misconceptions about Kobe and the CMB that still persist in pop science today.
I agree completely. Let's make sure the historical and scientific record is absolutely clear here. The first major misconception is that Kobe photographed the instant of the Big Bang itself. It did not.
Right.
It measured relic radiation from recombination roughly 380,000 years after the Big Bang occurred.
And the second misconception is that the CMB map shows galaxies already formed. As we discussed, that's entirely false. The map merely shows slight density variations in a hot, early plasma long before the first stars or galaxies ever ignited.
Yep. The third misconception is tied to the title of our source book. People often assume cosmic wrinkles are literal space-time creases or folds. They are not. Wrinkles is purely a metaphor for tiny temperature and density differences.
Misconception number 4 goes back to our guides for this dive. Media narratives often imply George Smoot made this discovery alone. That is demonstrably false.
Very false.
This was a monumental collaborative team effort, heavily involving John C. Mather, the instrument teams, data analysts, engineers, and the entire NASA Goddard community.
Misconception number 5 is more theoretical. Many assume Kobe proved every detail of inflation. Not true. It supported broad inflationary expectations, but no single definitive inflation model was uniquely confirmed by Kobe alone.
And finally, misconception 6. That WMP and Planck replaced Kobe's historic role. We just covered this, but to reiterate, they absolutely did not. They refined and expanded upon Kobe's foundational discovery, transforming that initial detection into the era of high-precision cosmology.
Clearing up those distinctions is vital for truly appreciating the science.
So to bring this all together to a final synthesis, how did we get here? It wasn't one magical event that instantly formed the cosmos. It is an extraordinary chain of physics.
Step by step.
Right. Tiny primordial variations, possibly born from microscopic quantum fluctuations, were imprinted as density differences on the early universe. As the universe expanded, gravitational growth took over. Non-baryonic dark matter provided the essential gravitational scaffolding, slowly pulling ordinary gas into deep potential wells after the radiation cleared.
Yep.
And over billions of years later, astrophysical processes ignited those collapsing gas clouds into the first stars and galaxies. Jointly, this incredible chain of physics explains how an extremely smooth young universe developed into the staggeringly complex observed structure we live in today.
It is perhaps the most profound realization in modern science. The vast cosmic web of galaxies we observe today, including the one we currently inhabit, was dictated by the microscopic, invisible conditions of the universe's absolute infancy.
Which is just, it's mind-blowing. And as we close this journey, I need to explicitly state that this deep dive is an independent COSMORA HQ book overview and audio podcast. It is not an audiobook, narration, adaptation, abridgment, authorized edition, or substitute for lawful access to the original work. Subscribe to COSMORA HQ for more authentic, source-based science and intellectual podcasts. Share your perspective in the comments, and share this episode with an intellectual friend who enjoys exploring the deepest questions about our universe.
If the universe began almost perfectly smooth, which part of its journey from tiny variations to galaxies do you find most extraordinary?